Welcome everyone to Routing and Switching. Today we'll be studying module number 7. We're going to be talking about DHCPv4 and IPv6 review. Now the main topics that we'll be discussing in the first part of this lecture are the DHCPv4 concepts. We're going to explain how DHCPv4 operates, how it works in a small to medium-sized business network. We're going to configure Cisco IOS to be a DHCPv4 server, and we're also going to configure a DHCPv4 client. DHCPv4 concepts. Now, DHCPv4 basically assigns IPv4 addresses and other networking configuration information dynamically. So as you guys are pretty aware of, every time we need to learn an IPv4 address automatically, we're just basically dealing with DHCPv4. Now, because desktop clients typically make up the bulk of network nodes, DHCPv4 is extremely useful and time-saving tool for network administrators, and that is mainly because you don't actually need to configure an IP address on every single one of the client machines. Now, in order for this to work, we obviously need a dedicated DHCPv4 server, which is scalable and relatively easy to manage. However, in a small branch or small home office location, a Cisco router can be configured to provide DHCPv4 services without the need for a dedicated server. Cisco IOS software supports an optional, full-feature DHCPv4 server. So I'm pretty aware that you guys have studied many courses here at CIT that requires you to configure DHCPv4 server. However, the main focus of the courses that you guys have done so far were basically to configure a Microsoft Windows Server 2016 or 2019 to be a DHCPv4 server. That is a possibility. The other possibility would be to just basically utilize one of the networking devices to assume the role of a DHCPv4 server, which is exactly what we'll be studying in this session. Now, the DHCPv4 server is responsible for dynamically assigning or leasing an IPv4 address from a certain pool of addresses for a limited period of time chosen by the server. So we just basically specify a pool of addresses, which is just basically a bucket with a whole bunch of addresses that will be available for our server to assign IP addresses. Client leaves the information from the server. So after requesting the information from the server, the client will just basically lease that address for an administratively defined period, which is usually 24 hours. Administrators configure the DHCPv4 servers to set the lease to time out at different intervals. When the lease expires, the client must ask for another address, although the client is typically reassigned the same address. Now, DHCPv4 works in a client-server mode. So if you guys remember from your networking essentials or introduction to networks classes, the role of a client and server, the client is just basically the machine which is responsible for requesting some type of service, and the server is just basically responsible for making these services available for the client. Now, when a client communicates with a DHCPv4 server, the server assigns or leases an IPv4 address to that client. Now, the client connects to the network with the leased IPv4 address until the lease expires. So that address which is assigned for the client can be used for that specific amount of time. When the time is over, the client just basically need to contact the DHCP server again and just basically ask for the lease to be extended, which is just basically equivalent if some of you guys rent a house or an apartment, you know that after the end of the lease period, you basically need to request the owner of the property or the property group or whatever, whoever it is, to renew the contract. And this is just basically an analogy of how the DHCPv4 works as well. Once the time is up, we just basically need to find a way to renew the address, and that's how the DHCPv4 mechanism works. Now, when the lease expires, the server returns the address to the pool where it can be reallocated as necessary. Steps to obtain a lease. Now, how does the client request to obtain an IP address? The client will just basically send an initial discovery message. This discovery message is just basically a shout out to the world asking for a server to assign it an IPv4 address. Now, all the 4 steps in a DHCPv4 transaction, I would say, is just basically comprised of the DORA, D-O-R-A. So just basically stands for Discover, Offer, Request, Acknowledgement. Just like mentioned, the Discover process is the first initial message that is sent by the client in order to try to reach out a server. This is a broadcast message. It's sent out every segment in the LAN, and just basically every single DHCPv4 server will listen to the message and will just basically reply back with an offer message. Now, this offer message is just basically a message sent by the server informing the client that it exists and offering it an IPv4 address. Now, if the client is satisfied with the IPv4 address that was offered, the client will just basically reply back to the server accepting the address offer. Now, once the server receives the message from the client acknowledging that it has accepted the IPv4 address offer, the server will send a message back saying that it acknowledges that the client has requested to use that IPv4 address. It's just basically a very polite process. There are many messages involved. It's not just a single answer reply sort of thing. Now, prior to the lease expiration, the client begins a 2-step process to renew the lease if necessary. Once the client is over with the lease, the client can just basically send a request once again to the server before the lease expires, requesting the server to just basically renew it. Now, the server can just reply back saying that the request has been acknowledged and verifying the information and returning a DHCP ACK or acknowledgement. Now, let's talk about how do we configure a Cisco iOS device to be a DHCPv4 server. Now that we have a basic understanding of how DHCPv4 works and how it can make your job a bit easier, a Cisco router running iOS software can be configured to act as a server, a DHCPv4 server in this case. Now, the Cisco iOS server, DHCPv4 server, assigns and manages IPv4 addresses from specified address pools within the router to DHCPv4 address clients. Just basically the same way that a Windows Server 2016-2019 would be able to issue IPv4 addresses to clients, we can configure our Cisco iOS router to be a DHCPv4 address server and issue IPv4 addresses to client machines. Now, there is a step-by-step process of how to do that. The first step is we need to make sure we exclude all the IPv4 addresses from this pool. In other words, we need to remove all the IPv4 addresses that we do not want the server to give to any of the clients. Now, in order to do that, we just need to execute the command ipdhcp excluded address, and we just basically specify a low address boundary and a high address boundary in order to exclude a certain range of addresses. Now, if we just want to exclude a specific address, we don't need to specify the high address range. Just the IP address that we want to exclude would be sufficient. Now, the second step is to define a DHCPv4 pool name. We just basically need to give a name to this bucket of addresses that we're going to be assigning to clients. We can do that with the command ipdhcp pool, and we specify a pool name, which can be a generic name, just with some sort of meaning that would help us identify the range of addresses. Now we're ready to move on to the third step. In the third step, we configure the DHCPv4 pool. The address pool and default gateway router must be configured. Now that we have a bucket of addresses that our server can work with and can give addresses to clients, it is just a matter of specifying the options. Of course, we want our DHCPv4 server to be able to give the default gateway address to the clients. We want it to be able to give the DNS server address if necessary. So we can basically specify many options while configuring our DHCPv4 server. Some of them include the address pool, the router, the gateway with the command default router, the DNS server with the command DNS server, the domain name with the domain name command, and also we can specify the DHCP lease duration, and we can basically specify the number of days, hours, or even minutes that we want to specify, or even if it's infinite so it never expires. We can also do a NetBIOS Win server address with command NetBIOS name server. Now, just a configuration example. In this case, we're configuring our router 1 to be the DHCPv4 server. The first step is as follows. We specify the excluded addresses. In this case, we're excluding all the addresses from 1 to 9 and also the 254 address. After that, we can specify the pool with a name that makes sense to us. In this case, just giving it a name, LAN pool number 1, just to specify that these DHCP pool will be the pool of addresses available for our LAN number 1. After that, we can just basically specify the network that these DHCP address belongs to, the default router with the address of the default gateway that will be given by the DHCP server as well, the DNS server information, the domain name if it exists, and after that we can do an end just to go back to our privilege exec mode. Now, a few more commands that are available to us as well to verify the configuration of the server. We can do a show running config and specify we're interested in the DHCP section. We can also issue the command show IP DHCP binding to display all the IPv4 address to MAC addresses bindings provided by the server. The show IP DHCP server statistics to just basically display count information regarding the number of DHCPv4 messages that have been sent and received. Now, to verify the DHCPv4 configuration, as mentioned, we can issue the command show running config section DHCP that would just basically show all the commands that were entered in order to configure our DHCP server. In this example here, as we can clearly see, the commands that were entered were to exclude the addresses, in this case all the addresses from 1 to 9, to exclude the default gateway address if we wanted to give that to the default gateway. In this case, we're actually giving the number 1. Now we also specify the pool name and also the options. So we're specifying the network, the default router, which in this case is just basically the default gateway information, the DNS server, and also the domain name. Now, to verify the DHCPv4 bindings, which is just basically all the DHCPv4 leased addresses, we can use the command show IP DHCP binding, and that will just basically display the addresses that are being leased. Now, to verify the DHCPv4 statistics, we can issue the command DHCP server statistics to verify the messages that are being sent or received by these DHCP server, which in this case is just the router. And this will just basically display the count information regarding the number of messages that have been sent and received. Now, to verify the DHCP client received IPv4 addressing, we can also use the command ipconfig/all that would show all the information about the DHCP server on the client side. So this is just an output of how it would look like when we execute this command on a Windows operating system. We just basically type it in ipconfig/all, and that would just basically show the IPv4 address information. Now, the DHCPv4 service is enabled by default. That's why we just need to enter the commands. However, we can also disable these service using the no service DHCP global configuration mode command. By using the service DHCP global configuration command, we can re-enable the DHCPv4 server process. Now, whenever we don't actually need to have a router to be a DHCPv4 server, we can just basically disable the service. Just, that would basically uh, uh, increase security a little bit, because obviously these services not available on the given router. Now, in a complex hierarchical network, enterprise servers are usually located centrally. These servers may provide DHCP, DNS, TFTP, and FTP services for the network. Now, network clients are not typically on the same subnet as those servers. In order to locate the servers and receive services, clients often use broadcast messages. Now, we need to remember the nature of DHCP, and we need to remember that DHCP works with broadcast messages to understand the importance of this. Now, in the image, PC1 is attempting to acquire an IPv4 address from a DHCP server, which is right here on the other segment of the network, using a broadcast message. But as we know, a router is actually a Cisco device, or it's just a device that will just basically break a broadcast domain. What this means is every time that PC1 sends a broadcast message to router 1, router 1 will not forward to the other interface. That just basically means the broadcast message sent from PC1 will never be able to reach the DHCPv4 server without an extra step. And this extra step is just basically configuring router 1 to relay DHCPv4 messages to the server in a different network segment. Now, this relay function just basically means that router 1 will be able to take the broadcast message and basically forwards it out into another interface to the specific DHCPv4 IP address. Now, in order for us to configure this feature, we just basically need to go into router 1 and specify the command IP helper address and specify the IP address of the server in the different network. Now, in this case, we need to configure this into the interface that will be receiving the broadcast. Now, in the previous scenario, we've seen that router 1 was receiving this broadcast message into the interface gig 000, and that's why we are configuring IP helper address in this interface. Now, please note that this helper address that is specified in the command is actually the IP address of the DHCP server, even though it's in a different network. We can verify that this has been done with the command show IP interface. Specify the interface, we'll be able to see the helper address that has been configured. Now, DHCPv4 is not the only service that a router can be configured to relay. By default, IP helper address commands also forwards the following 8 UDP services, not only DHCP, but it will also forward time, TechX, DNS, DHCP PutP server client, TFTP, NetBIOS name, NetBIOS datagram, and so on. All right, let's talk about how we configure the DHCPv4 client. Now, there are scenarios where we might have to access the DHCP server through the ISP. In these instances, we can configure Cisco iOS router as a DHCP client. So remember that so far we configured our Cisco router to be a DHCPv4 server. In this case, we're actually studying the fact that the Cisco router can also be a client router, so we can obtain DHCPv4 information from the ISP. Now, in order to do that, we just need to go to the specific interface that we want to obtain an IPv4 address, and we need to type it in the command IP address DHCP interface. Now, in the image that we have here is a very similar topology of how we actually have what we actually have in our house. If you have ADSL, or whether you have NBN in your house. It's just basically similar to what happens here. Your router is configured to be a DHCPv4 client. You will just basically reach out to the ISP DHCPv4 server in order to obtain a public IPv4 address that will allow us to connect ourselves to the internet. Now, to configure an Ethernet interface as a DHCP client, we use the command IP address DHCP as mentioned before. Now, in the example that was given, we can just go to our small home office network router, and we can go to the interface which is connected to the ISP infrastructure, and we issue the command IP address DHCP. We can do a no shutdown to bring the interface up. To verify that this has been done, we can issue the command show IP interface gig001. Now, in our home networks, we actually have a slightly different network in a sense that the protocol that is used to contact the ISP server will also require authentication. So for our home routers, we actually need to provide a username password as well, so that our home routers is actually able to authenticate themselves with the ISP router before actually obtaining an IP address. Home routers are typically already set to receive this IPv4 address information automatically from the ISP. This is so that the customers can easily set up the router and connect to the internet. In the figure below, we actually see that the default WAN setup page for Packet Tracer wireless router is just basically to obtain an automatic configuration address from the ISP. Now, for some routers, we actually need to do it manually, especially those routers that you buy separate from your ISP contract. Usually requires us to go to the router and do some basic configuration before we actually able to connect it to the internet. And while doing that, we need to specify DHCP to obtain an IP address from the ISP itself, and we also need to specify most of the time a username password to authenticate ourselves with the ISP. Okay, let's move on to our IPv6 addressing review. This is a very important topic for next week, especially because next week we're going to be discussing about DHCPv6. But before we actually able to do that, we need to discuss about IPv4 addressing. Now, these are the things we're going to be talking about IPv6 in this lecture. So we're going to talk about IPv6 address types. We're going to talk about the global unicast address, link local address, static configuration, dynamic addressing for IPv6 global unicast addresses and link local addresses. And we're also going to talk about the IPv6 multicast addresses. Let's start things off with the IPv6 address types. Now, in IPv4, we have a very interesting type of message, which is the broadcast message. And a broadcast message is just a message that is sent out to every single host within the local area network. Now, the only thing that we don't have in IPv6 compared to IPv4 is the broadcast message. Now, IPv6 actually provides us unicast, multicast, another special type of communication called the anycast. Now, the unicast is just the same as IPv4. It's just basically a message that uniquely identify an interface on an IPv6 enabled device. You want to send a message from one machine to another machine, you're most likely going to use a unicast message. We also have the multicast message, which is just basically a message sent as a single packet to multiple destinations, similar to what we have in IPv4. Now, the only thing here that we have in IPv6, we don't have it in IPv4, is the anycast message. And this is an IPv6 unicast address that can be assigned to multiple devices. A packet sent to an anycast address is routed to the nearest device having that address. So this is a very nice touch, a very nice feature of IPv6 address types. The anycast address will actually allows us to assign the same address to multiple devices And anytime you want to send a message to this specific address, it goes to the device which is closer to you. Now, just like I mentioned before, unlike IPv4, IPv6 does not have broadcast addresses. I cannot stress these enough. It doesn't have a broadcast address, okay? Now, in IPv6, we actually have something nice if we want to reach out to all the nodes within a local area network, and that is also known as the all nodes multicast address. It gives the same result as the broadcast message. The only difference is it's not called a broadcast message, to be clear. Alrighty, let's review about the IPv6 prefix length. The prefix length is represented in slash notation, very similarly to what we have in the network subnet mask of our IPv4 address. It just basically indicates the network portion of the IPv6 address. Now, the IPv6 prefix length can range from 0 to 128. The recommended IPv6 prefix length for LANs and most other types of networks is /64. Now, it's strongly recommended to use a 64-bit interface ID for most of the networks. This is because stateless address auto configuration (SLAAC) uses 64 bits for the interface ID. It also makes subnetting easier to create and manage. Now, we're going to talk about stateless address configuration (SLAAC) in a few more slides to come, so stay with me a few minutes more. Now, unlike IPv4 devices that have only a single address, IPv4 addresses typically have unicast addresses. In this case, IPv6 usually have two types of addresses. We have the global unicast addresses, the GUA or GUA, and we have the link local addresses, the LLA or link local address. Now, the GUA or GUA is similar to a public IPv4 address. These are the ones that are globally unique and they are routable through the internet. Now, the link local addresses, they are required for every IPv6 enabled devices and they are used to communicate with other devices on the same local link. Now, linked local addresses are not routable and are confined to a single link. Now, the linked local addresses, they are similar to a private IPv4 address. However, the linked local address or LLA, they are confined to a single link. Other type of IPv6 addresses include the loopback address, which is the colon 1, which is just basically equivalent to the 127.0.0.1 that we have in IPv4. It's just basically a loopback address. We also have the unique local addresses as well that we're going to be discussing a few slides more. The IPv6 unique local address, which is all the addresses in the range of FC00::/7 to FDFF::/7, they have all some similarity to the 1918 or all the private addresses for IPv4. But there are some significant differences. For instance, the unique link local addresses are used for local addressing within a site or between a limited number of sites. The unique local addresses can be used for devices that will never need to access another network. Unique local addresses are not globally routed or translated to a global IPv6 addresses. Now, many sites use the private nature of 1918 addresses to attempt to secure or hide their network from potential security risks. This was never the intended use of unique local addresses. Now, IPv6 global unicast addresses, or the GUAs, they are globally unique and routable on the IPv6 internet. Currently, only GUAs with the first 3 bits of 001 or the 2000::/3 are being assigned. So pretty much everything we have nowadays on the internet of GUAs, they all start with the 2000 range ::/3. Now, currently available GUAs begin with a decimal 2 or a 3. This is only 1/8 of the total available IPv6 address space. So pretty much everything that we see nowadays, they will all start with the 001 in the global routing prefix. In other words, the range can be from 2000 up to the way to 3FFF. Now, another important thing to note here in the IPv6 address structure is that we have the global routing prefix, we have the subnet ID, and we also have the interface ID. Now, the global routing prefix is usually the first 48 bits, so that would be the /48. All the bits between the 48 to 64, they would be the subnet ID, which can be used to create subnets, and all the rest of the bits from the 60 /65 all the way to 128, they are the interface ID. Now, the global routing prefix is the prefix or network portion of the address that is assigned by the provider. Just like the public IPv4 address, it's given by the ISP to the customer or the site. The global routing prefix will vary depending on ISP policies. Now, the subnet ID is the field in the area between the global routing prefix and the interface ID. Just like I mentioned already, it can be used by the organization to identify the subnets within its sites. The interface ID, which is last but not the least, is the equivalent of the host portion of the IPv4 address. It's strongly recommended that in most cases /64 should be used, which create a /64-bit interface ID, just basically telling us we have 64 bits to assign to our host machines. An IPv6 link local address, or the LLA, enables a device to communicate with other IPv6 enabled devices on the same link and only on that link alone. Packets with a source or destination LLA cannot be routed. Just basically means they cannot go to the internet as they are. Every IPv6 enabled network interface must have a link local address. If a link local address is not configured manually on the interface, the device will automatically create one, and we'll see how they automatically give them an address in a few slides. Now, the IPv6 LLAs, they are in the FE80 : 10 range. So pretty much everything that starts with FE will be in the link local address range. Alrighty, let's talk about the GUA and LLA static configuration. Pretty simple, very straightforward step to configure an IPv6 address on an interface. Just basically need to go to the interface of the router and type it in the command IPv6 address. Now, in contrast with the IPv4 address assignment, in IPv4, we don't need to specify the subnet mask with the decimal notation. For IPv6, we can just specify the prefix length with the / notation, and that's all that we need. Okay, so specify the IPv6 address, specify the / prefix length, that's all that we need. Once again, we need to make sure we bring back the interface by issuing the command no shutdown on the interface that we configured. Now, manually configuring IPv6 addresses on the host machines are very similar. Just need to go to the IPv6 protocol properties and specify the address and the prefix length. Now, the GUA or LLA of the router interface can be used as the default gateway, but the best practice is to use the LLA. Configuring the LLA manually lets us create an address that is recognizable and easier to remember, because after all, we just basically gave it ourselves. Now, the LLAs can be configured manually using the IPv6 address, so the same way. The only difference between the LLA assignment and the standard IPv6 address assignment, the GUA, is that we type it in the keyword link local in front of the IPv6 address when we're configuring it to be a link local address. Dynamic addressing for IPv6. GUAs. Now, it's very inconvenient if we have to assign IPv6 addresses statically for every single device. So there's actually a way around that with the GUAs dynamically addressing themselves through ICMPv6 messages. Now, the ICMPv6 messages that are used in order to assign themselves an IPv6 address are the router solicitation and router advertisement. Basically, the RSA and RA messages. The RS solicitation message is sent by the host to discover the routers. It's just basically a message that the client machine will send out asking if there's any router in the segment. Now, the router will send a message back to the client called the router advertisement, which is a message that the router provides useful network information. This network information includes the network prefix and the prefix length, as well as the default gateway and DNS and domain name, if existent. Now, the RA can provide three methods for configuring an IPv6 GUA. Now that we have the basic network information that we obtain from the router, we can just basically assign ourselves an IPv6 address. Now, there are three methods for doing that. The one which we're going to be focusing in this session is the SLAAC method. Now, there are other two methods, the SLAAC with stateless DHCPv6 server and the stateful DHCPv6 with no SLAAC. These two latter ones we're going to be discussing in our upcoming session. Okay, let's talk about the SLAAC method. Now that we have obtained from the router with the router advertisement all the necessary information we need to be able to connect ourselves to the network, we are now able to proceed and create ourselves an IPv6 address. Now, the prefix which was obtained from the router advertisement would just basically contain the prefix, okay? Would just basically contain the necessary info we need to be able to be in the same network as the router. Now that we have the prefix and the prefix length, we just basically need to find a way to give ourselves an interface ID. This interface ID can be given to ourselves using two methods. The first one of them is the EUI64 and the second is the random 64-bit number. When we do the EUI64, we just basically utilize our MAC address and we do some extra steps with that, and then we assign the interface ID address based on that. With the random 64-bit number, it is just basically a randomly assigned number which our machine or our router will assign to itself. Now, the router advertisement can instruct the device to use both SLAAC and stateless DHCPv6. Now, if SLAAC is used, it will just basically do its thing and will create the address itself, and that's all. Now, if stateless DHCPv6 server is present, what's going to happen is the client will give itself an IPv6 address, but in order to obtain extra information such as the default gateway, the DNS information, domain name, and everything else, it will actually go to a server to do that. All right? Now, a stateful DHCPv6 is similar to the DHCPv4 in a sense that we just basically obtain all the information straight away from the server. When the router advertisement message is either SLAAC or SLAAC with the stateless DHCPv6, the client will generate its own interface ID. Now, the interface ID can be created using EUI64, as I already mentioned, or the randomly generated 64-bit number. Now, within the EUI64 process, defined in the IEEE Extended Unique Identifier, the process is as follows. So the 16-bit value of FFE is inserted in the middle of the 48-bit Ethernet MAC address of the client. So you just basically take the 48-bit MAC address of the client machine, we split it in half, we pad it with this FFFE, hexadecimal sequence, and we just basically then proceed to change the 7th bit from 0 to 1. So we just basically reverse the 7th bit of the client MAC address. After that, we just basically assign ourselves our interface ID, and based with the extra information obtained from the router advertisement, we will then have an IPv6 address. Now, depending on the operating system, a device may use a randomly generated interface ID by using the MAC address and the UI64 process. However, beginning in Windows Vista, Windows uses a randomly generated interface ID instead of the UI64. So all the newest versions of Windows, they will just basically assign a randomly generated IPv6 address. If you actually try to compare this address with the MAC address, they pretty much have nothing to do with themselves. And that is because the IPv6 address was created without the MAC address into consideration. Dynamic addressing for IPv6 LLAs. Now, all IPv6 interfaces must have an IPv6 LLA. Like IPv6 GUAs, LLAs can be configured dynamically as well. In other words, that means we can also create a link local address dynamically using the UI64 process or the randomly generated 64-bit number. Operating systems such as Windows will typically use the same method for both SLAAC created GUA and dynamically assigned LLAs. So basically, if you have a Windows machine that is using the UI64, you see that they are very similar except for the prefix. Now, if there is a random 64-bit generated interface, they are very similar as well. The only difference is that they are not related to the MAC address at all. Now, Cisco routers automatically create an IPv6 LLA whenever a GUA is assigned to the interface. By default, the routers use UI64. In other words, it just basically means they will be based on the MAC address. If you execute the command show interface and then specify the interface ID, be able to see the MAC address and also the IPv6 address with the show IPv6 interface brief. In this case that is shown here, we can easily identify that the IPv6 address, link local address in this case, was actually created based on the MAC address. As we can see, it's just basically using UI64. It's just basically split the MAC address in half, padded the middle with FFFE, and inverted the 7th bit from 0 to 1, which caused the second hexadecimal character to become a 2 instead of a 0. Now, Cisco routers automatically create an IPv6 LLA whenever a GUA is assigned to the interface. By default, they use the UI64. IPv6 multicast addresses. Now, IPv6 multicast addresses, they all have the prefix FF00::/8. There are two types of IPv6 multicast addresses: the well-known multicast addresses and the solicited node multicast addresses. Multicast addresses can only be destination addresses and not source addresses. It's a very important observation. Now, well-known IPv6 multicast addresses, they are assigned and are reserved for the predefined groups of devices. There are two common IPv6 assigned multicast groups. We have the FF002::1, just basically specify all the nodes multicast group. So whenever we want to reach out to all the nodes within a specific group, we can specify the all nodes multicast group address. Now, whenever we want to reach out to all the routers, we can specify the address FF02::2. This will be a message that is going to be sent out to all the routers within a certain multicast group. Now, a multicast group that have all IPv6 routers join, which is the all routers multicast group, the router becomes a member of this group when it's enabled as an IPv6 router. And just a quick review here, the way that we can enable a router to be an IPv6 router is through the command IPv6 unicast routing command. A solicited node multicast address is similar to the all nodes multicast address. It's just basically a message that we want to send out to all the machines connected to the segment. Now, a solicited node multicast address is mapped to a special Ethernet multicast address. The Ethernet NIC can filter the frame by examining the destination MAC without sending it to the IPv6 process to see if the device is the intended target of the IPv6 packet. This is everything that we learned in this module. These are the required activities for this week. So for this week, I'm expecting you guys to complete Packet Tracer on configuring DHCPv4, implementing DHCPv4, and also a lab 7.4.2, which is just basically implementing DHCPv4. Next week, we're going to go to module number 8, and we're going to talk about SLAAC and DHCPv6 concepts.